Hello, everyone. I'm Feige Wang, a postdoc at the University of Arizona. First, I would like to thank for organizing this wonderful virtual meeting, because in this time, we cannot go to observe this meeting. We cannot travel, and this meeting gives us a great opportunity to catch up the latest studies. So today, we'll focus on the Reionization Era Quasars. Really find the rest of 8 quasars in the next coming years, and what kind of environment this quasar residing in, whether residing in the most overdense environment or a random field. Okay, so in the last couple decades, we have a good understanding of the density evolution of quasars from redshift 0 to redshift 6. Like the density peaks at redshift 2 to 3, and the drops and declines very fast from redshift 3 to redshift 6. But we have little information at higher redshift. That's one of our motivation. How to find those quasars? Since the discovery of quasars, there are many different techniques to find the highest redshift quasar. In the early time, people using the radio technique, and then followed by optical. But if you go to Reionization Era quasar, you have to use the infrared, because the lemma alpha line redshifted to close to 1 micron or even beyond 1 micron. So we really needed the infrared wide imaging surveys. Fortunately, in the past few years, there are many imaging surveys. I will not go through each survey, but these surveys provide us a 20,000 square degree of the sky with infrared imaging, and our selection are based on this. I will not talk about the selection details. I will go to see the results directly. I wanted to first highlight 2 discoveries made by us very recently. One is redshift 7.52 quasar. We just published this quasar EPG letter in last month, and it has a wonderful Hawaiian name, Panua Annan, which means the unseen spinning source of creation surrounded with brilliance. This quasar hosts a 1.5 billion solar mass black hole and challenging the black hole growth history. And the other quasar is discovered very recently, which is a luminous quasar at redshift 7.62. And here shows the 2D spectrum of this quasar. We can clearly see the lemma break at 1.05 micron. So this is the new quasar redshift record holder. Besides this really high redshift quasar, we already have a relative sizable quasar sample at redshift beyond 6.5. To date, there are about 60 quasars at redshift 6.5, allows us to do some statistical studies, and among them, 8 quasars at redshift beyond 7. So among those quasars, more than 30 quasars discovered by us, and 5 of the 8 quasars at redshift 7 beyond 7 are discovered by us. So this is a really good opportunity for us to do statistical studies. But our selection currently is not complete at a really high redshift, but it's relatively complete from redshift 6.5 to redshift 7. So we can really, for the first time, to measure the density of quasars at this redshift. Here shows the quasar luminal function we measured based on this quasar sample. As shown in the orange line and the dots. I also show the redshift 6 quasar luminal function here. As a comparison, you can see that the density or the normalization of luminal function declines a lot, which means the quasar density drops very fast. So if you integrate the luminal function, you got the density evolution. That's our measurement. It's about 0.4 per gigaparsec cube. So from this plot, you can see that the decline rate seems increasing towards to higher redshift. If you extrapolate this decline rate to higher redshift, that means there are only 1 quasar in the observable universe at this brightness. So we really wanted to find those really first quasar host billion solar mass black holes. How to find them? Fortunately, there are several surveys in the coming years will provide a excellent data set for finding those quasars. The LSHT survey will allow us to find out several thousand quasars at redshift beyond 6, and about 100 quasars at redshift beyond 7. But if you wanted to go higher redshift, you really need the infrared surveys from the WFIRST or the Raman telescope and the Euclid telescope. But even with those surveys, we can still only find like an order of 10 quasar at redshift around 8. And we probably can find one quasar at redshift 9, or we probably cannot find them if the decline rate is keeping increasing. So we really want to find those quasars in the next coming year with these new surveys. All right, so since the quasars density is so low, they must reside in the most of the bias halos, and they should be residing in the most overdense environment. So how to probe the environment of those quasars? There are many efforts in the past couple of years to studying the environment with both HST and the ground-based imaging to searching the lemma-break galaxies around quasars. But the HST field view is too small. It's much smaller than the size of a protoclass, which could be even up to several tens megaparsec. The other problem is the lemma-break galaxy redshift uncertainty is pretty large, so the signal is washed out by large projection effect. And also, if you only target few quasars, it's strongly affected by the cosmic variance. In order to solve these difficulties, we can do the deep wide field imaging, and we can use the narrowband imaging rather than the broadband selection to narrow down the redshift of the galaxies, and then to pick up the galaxy directly related to the quasar. There are several works done recently, but as we have already seen that from GT's talk in this morning, the quasar broad lines usually has a really large blue shift, so they cannot represent the systemic redshift of the quasars. If you do not have accurate redshift, which means you probably can miss the really lemma alpha emitters close to the quasar, like here. So two examples. This is a quasar real redshift, but initially before doing the narrowband imaging, the redshift is here. So the real lemma alpha emitter is close to the quasar is actually out of the narrowband, so you miss all the overdensity. And also we needed to do a larger quasar sample to do the quasar galaxy cross-correlation function to finally give an answer of the environment of those distant quasars. So in order to get the accurate redshift, we are surveying the C+ line from the host galaxies of all bright quasars at redshift beyond 6.5. Here are some examples. And fortunately, we got about more than 10 quasars can be probed by the narrowband imaging. We have done one observation for one quasar at redshift 6.63. As shown here, the lemma alpha emission of the galaxy at the quasar redshift is right in the center of a narrowband, and then we can select the lemma alpha emitters. We are using the Subaru to do the really wide field deep imaging. As a comparison, here is the HST field view. Here is the size of the full moon. So we are going down to about 25.5 magnitude also. And we really pick up overdensity. We really find it's overdensity surrounded by the quasar. Here is the central quasar. This map is a density map of the lemma alpha emitters selected using the Subaru HSA imaging. So you can see that the density is pretty high at the center, and the scale is really large. If you like only using HST coverage, it could miss the overdensity. And we also observed this quasar field with many other observations, the G7T dust continuum observations and the ALMA observations to get the C+ line of the galaxies in the quasar fields. As shown here, we have already discovered several galaxies at redshift close to the quasar, so which means this quasar is really residing in a very overdense region. This is our first example. We are designing a new filter to cover more quasars, which will be hopefully installed on this fall, and then we can study more quasars to finally get the cross-correlation function between quasars and galaxies, and to answer the question whether the highest quasars residing in the most overdense environment. Okay, I will summarize here. the quasar spatial density declines really fast, but we already have a statistical quasar sample at Redshift 7. We have already used this quasar sample to study the density evolution. We have used this quasar sample to study the IgM neutral fraction, as shown in Jin Yang's talk yesterday. And we now discover a new quasar Redshift record holder at Redshift 7.6. And we identified a large scale overdensity around the luminous quasar at Redshift 6.6. Yeah, I will summarize here. And thank you for your attention. I will be happy to take any questions.
Rebecca Bowler asks, can you say anything about the host galaxy of these bright quasars?
Yeah, sure. So those quasars, the host galaxy of those quasars are relatively bright. Like it hosts the star formation rate, and the star formation rate of those quasars are about several hundred solar mass per year, and the total dynamic mass could be 10 to 11 point something solar mass. But currently our resolution is not high enough to study the kinematics, but we do see some really nice velocity gradient of some of the quasars. So yeah.
Okay. Seiji Fujimoto asks, how many targeted quasars at z equals 6.6 show the overdensity?
So currently we only target one quasar. So we will target more, and I can answer you this question in the next few years, I think.
Alyssa Drake asks, signs of carbon-2 outflows?
That's a really good question. So from the individual observations, like the C+ line of individual quasars, we did not see any evidence of the outflow, but we are trying to stack all the C+ spectra of these quasars, and hopefully we can see some outflow signature. But based on the UV lines as shown from GT's talk, those quasars could have really large outflow or driving by the radiation, but I'm not sure whether we can see the C+ outflow.
Okay, so Jarit Mati asks, I know it's low number statistics at Redshift 7.5, but is there a selection effect against Redshift 7.2 to 7.5 quasars? For example, a combination of available BV filters.
Yeah, that's a really good question. So currently, like at Redshift below 7, we are quite complete, and there's little bias. But at Redshift higher than that, we do have some bias, because those 7.5 quasars, like the dropout, its dropout is optical. You basically see nothing in all the optical imaging. But for quasar at Redshift 7.2 also, you probably can still see some flux in the Z band or pan-star Y band. So for such kind of quasar, we haven't followed up yet. But we are mostly focusing on the totally optical dropout. So at the Redshift beyond 7.2, we probably have some bias to 7.5 quasars, and we missed some 7.2 quasars. But we will follow up them later.
Okay, and Fabio Vito asks, can you share the ID of the QSO of which you study the environment? I think I missed it.
Sure. I didn't put it in the talk, but I will send you the ID later.